really happened? Either we measured wrong in the sense that maybe we were supposed to make sure our product was dry, but we waited when there was still some water left. Now we're getting a higher value than we expected. Maybe our product that we collected wasn't pure. So we end up with other things in there when we wait. Now it's heavier than expected, and we can get a percent yield greater than 100. But in general, our percent yield is less. The reaction might not go to completion. Some of them might have stayed soluble, stuff like that. Chapter 4, reactions in aqueous solutions. Electrolytes. What are electrolytes? They conduct electricity when dissolved in a solution. How well something is, how strong of an electrolyte is based on the number of ions that are there floating around. So a high concentration of ions means a strong electrolyte. We did the chapter on acids, bases. When we looked at weak acids, what does it mean to be a weak acid? It means there's strong attraction and only a few of them ionize, right? Most of them stay together as HA. Only a few H positives and A minuses are produced. So when we're talking about our electrolytes, a weak acid would be a weak electrolyte. It might dissolve, but since it doesn't ionize, doesn't separate, it ends up not having a lot of ions present, so we end up being a weak electrolyte. Something that's a strong acid that ionizes completely, we get a lot of ions, that is a strong electrolyte. Hydration, what do we mean there? Right. Something like this, right, where we have our ions, depending upon the charge of the ions, will be how the orientation of our water molecules. Here we have a Na plus ion, it's positively charged, so the negative side of the oxygen molecules are attracted in. Here we got our negative, our hydrogen side is surrounding that. Right. Precipitation reaction and solubility rules. What were the solubility rules we needed to know? All right. All nitrates are soluble. All group 1 metals, usually we're just talking about lithium, sodium, and potassium, and all ammonium ions, or compounds are too. There's a couple other ones in there, all acetate, all chlorates. These are the ones that commonly show up there. All right. So a precipitation reaction, all right. We'll talk about that when we get to our types of reactions. What is the difference between the molecular equation, ionic, and net ionic equations? Molecular is the standard one, the normal one that we're used to, right? We might have something like something like this. We might have aqueous. All right, so we have this. What would my products be? We'll say this is a precipitation reaction. What? NaNO3 too? No, why not? I got to think about charges here, right? Na is +1, Cl -1, Ba is 2+, nitrates -1. So I get NaNO3. And what else do I get? I can put a 2 there just to balance it off, 2 there. How do I figure out who my precipitate is? Do I know the rule on barium and chlorides, if it's soluble or not? No, I don't. But I don't need to. Why? I know that sodium nitrate is going to be aqueous. Since they told me it's a precipitation reaction, that means my BaCl2 is going to be my precipitate. Right? So that's a molecular equation there. What would the ionic equation look like? This is what we don't usually do this one, right? We either do molecular or net ionic. What does an ionic equation look like? We take anything that's aqueous and we separate them from each other. All right, so those are going to be all separate. We're going to get, but now since the BA changed, we're going to keep that one together. So the net ionic equation, right? We just take the ones from each side that are the same. What's the same on each side? Our 2 NAs, our 2 NAs, our 2 NO3s, our 2 NO3s. So now what are we left with? We're left with our 2CO minus plus BA2 plus. We could write aqueous for those. All right, and then I have my net ionic equation. Doesn't matter the order here. What does matter is me including the charges. If it's ionic, I know the charges are there. All right, I got to make sure I show those charges there. All right, so that's our molecular equation, our net ionic, and then our net ionic equation. Acid-base neutralizations, we're going to cover that more in chapter 15, 16. Redox reactions, we'll cover that more again in 18. But what were oxidation numbers? What were those? We had like a set of rules. That set of rules was based on if atoms are bonded together, we're assuming complete transfer of electrons. That works for ionic because that's easy, right? Whatever the charges are, that's going to be the oxidation number. Where it can also help us is with covalent compounds. So let's say we had this right here. And I asked who was oxidized and who was reduced. How could I get that? Well, I got to assign oxidation numbers for that. Elements in their uncombined state, what is their oxidation number? 0. So 0, 0. Now I have H2O. What were my rules? Oxygen is almost always -2, and hydrogen usually +1. And that works here, right? Right, there's 2 H's. That'll be a total of +2, a total of -2. Then we even out. So who was oxidized and who was reduced then? We just had that chapter. We got it. Oxygen was reduced. Right, it went from 0 down to -2. And our hydrogen was oxidized. Oxidizing got its name by things reacting with oxygen, right? This was oxidized because it was reacted with oxygen. And now they had that term and they expanded it so it's not just with oxygen but other things where the charge goes from 0 to +1 and the oxygen being reduced. Types of reactions. Combination reaction. What's like the format for that? A plus B yields AB. All right. How about decomp? In general, which one of these would have a positive delta S? Decomposition. Why decomposition? Goes from 1 mole to 2 moles. A little bit of assuming states of matter here, but in general, like that would have a positive delta S. Delta S is a measure of entropy, how much disorder. We're going from 1 particle to 2 particles, more disorder. All right, combustion reaction. We always have a fuel that has at least carbon and hydrogen in it. Right. We always add oxygen, we get carbon dioxide and water vapor. If we were to balance these, we balance oxygen last, right, because it shows up in multiple places. If we're having trouble balancing, we put a 2 in front. Single replacement reactions. Our whole study of chapter 18 was single replacement reactions. right? We might have something like, what am I going to get out of this if I know a reaction occurs? The idea here is it's a redox reaction. Somebody's going to lose electrons, somebody else is going to gain electrons. MgNO3, is that correct? What do I have to factor in? Then I can put a 2 there, 2 there. So that right there is a single replacement reaction. Who is oxidized, who is reduced? What do I have to assign? Here, NO3 I know is -1. I could keep NO3 together because NO3 shows up on this side, unchanged. So I know that that's not going to change. My Ag, what's the charge on that be? +1. My Mg, 0. My Mg on this side is now +2 and 0. So who was oxidized? Mg went from 0 to +2. Who was reduced? All right, Ag from +1 down to 0. All right. If I was to do a net ionic equation for this, what would I get rid of? The nitrate, the NO3, right? Because the AgNO3 is aqueous, the magnesium is a solid. Now the magnesium has replaced the silver in the solution. The silver is now a solid, and the magnesium went from solid to aqueous. All right, double replacement, displacement. We showed that one above. That was the precipitation reaction. Disproportionation. All right. Here is a disproportionation reaction. All right. Let's assign oxidation numbers here. Oxidation number, let's start with the O2. That's the easy one, right? What do we got? 0. What do we have for the H2 and O and H2O? +1, -2. What about H2O2? This is a peroxide. There was a special rule for this one. O is -1, H is +1. All right. Who was oxidized, who was reduced? Oxygen was oxidized, and oxygen was reduced. Right? It went from -1 to -2, and from -1 up to 0. So here, since oxygen was both oxidized and reduced, that's where we get that. That is a disproportionation reaction. All right. Concentration, molarity, dilution. All right. Molarity is a really convenient for us because we're experts at multiplying molarity times volume. What does that get us? Moles, right? So that's really useful to us. How do I use that with dilutions? What is the general idea of a dilution? I add water, so what happens to the volume? Increases. What happens to the concentration? Decreases. What stays the same? The number of moles of our solute that's in there. That's why I can do M1V1 equals M2V2. That is just telling me my mole stays constant. I'm adding water, so my volume increases at the same rate as my concentration decreases. I still stay with the same number of moles. Why can I use that idea for acid bases then? Right? I could say that MAVA equals MBVB. Because at the equivalence point, my moles of acid equals moles of base, right? 2 moles equaling each other. Just like here we only have one solution that's the same solute, just getting diluted. But in our acid bases, there we end up neutralizing each other at the equivalence point when the moles of acid equals moles of base. Right. Gravimetric analysis. It's kind of just fancy stoichiometry. Usually what will happen is you'll have a sample that has some, say, iodine in it. You dissolve it, you use something to precipitate out all the iodine, get your product, filter it, rinse it. Why do you rinse the to get any leftover ions out of it? So it's just what you have. And now you can take that, dry it, weigh it, figure out how much iodine is there, to figure out how much iodine you started with. It's number crunching using mostly stoichiometry there, and knowing about percent composition and that kind of thing. Acid bases we talked about. We'll talk about more. Redox titrations. Those are those like really ugly equations. They have like 16H plus something you've never heard, like 2MnO4 minus, like, and it ends up just being an oxidation reduction. The way that we solve these is using molarity times volume to get our moles, right? Just like we would if somebody gave us grams. We use grams to get moles, and then we use stoichiometry. Here we use molarity times volume to get moles, and then we just do regular basic stoich from there. Right. As long as we're comfortable with molarity times volume is moles. Make sure here, if we're multiplying those two together, since our molarity is moles per liter, our volume has to be in liters so that we get moles out of it. When I use my M1V1 as M2V2, my volume could be in milliliters. Because if it's milliliters on both sides, I would just end up dividing both sides by 1,000, which cancels out. Chapter 5. You gonna do this another time? Yeah. All right. Atmospheric pressure. What's atmospheric pressure? Pressure, all the gases that are above us pushing down on top, colliding with us, right? We end up with our 1 atm, 760 mmHg, 101.3 kPa. All of those are the same thing, right? We'll get those on our equation sheets. We're fine. Yeah.
How often do you think we're going to end up seeing, I know you're going to talk about it yet, but like the barometer and we're going to be like calling on stuff?
No, but they might talk, like allude to it, or maybe a picture on a multiple choice question. Okay. My barometer was a little inappropriate, so I made a picture of it. All right. So a barometer, we take a full, basically like a huge test tube, a udiometer. We fill it with, invert it, and we end up with this. So gas pressure is colliding, pushing down on there, trying to push it up into the tube. What's gravity doing? Trying to pull that down so that the levels are equal. All right. This is a measure of how much our atmospheric force is. We can look at the height, and that is our mmHg. If I took this up in a hot air balloon, what would happen to my height? It would decrease. Why? There's less gases as I go up in the altitude. There's less gases pushing down, so pressure lowers. So I'm going to end up with a lower value there. How about a barometer? A manometer. Manometer.
That's what I'm saying.
All right. Our manometer here, all right, we have a sample of gas. Is that sample of gas at a higher pressure or lower pressure than atmospheric pressure? Atmospheric pressure is pushing down on this one. This gas is pushing down on that side. Who's pushing harder? The gas is, right? Because it's trying to push that out of the tube. If I heat this up, what happens? Particles move around fast. They're going to collide more here, and they're going to push. That height is going to increase. Right. If they're at the same level, obviously they have equal pressures. Right. All the gas laws, the ideal gas law, that is one idea. That is one concept. Right. The combined gas law, P1V1 over N1T1 equals P2V2 over N2T2. That stems from, right? These are really interchangeable because what this is saying is that these two are equal to each other. They're equal to a constant value. That constant value, if I rearrange this, is just that R value. Here, it doesn't matter what units I plug in. Oh, when would I use the PV equals nRT versus my combined gas law? PV equals 1RT is one situation. Nothing's happening. I know 3 of these variables. I'm trying to get the 4th. Right? R is a constant value. Here, something changes. I heat the sample up. Well, what does that do to the pressure? Right? I decrease the volume. What does that do to the pressure? Something like that. Here, it doesn't matter what units I use. Actually, what are the only units have to be in? Kelvin, right? Temperature has to be in Kelvin. But all those other units are fine, as long as they're the same on each side. PV equals nRT, since we're using R in liter atmosphere per mole Kelvin, my pressure has to be in atmospheres. My volume has to be in liters, moles, and Kelvin. The R value they give to you, we can look it up on our sheets there. Rarely, but they might ask about density. And there you use your idea of density and molar mass. What we did is we rearranged PV equals nRT and put density in there. You could do that if you're comfortable, right? We know density is mass over volume, and our moles is mass over molar mass. Again, those are given to us. What we can do is substitute in for PV equals nRT. If I plug in my N, my moles, M over MM, right? Then I could rearrange this, move my MM up to this side, my V down to that side, and I end up with M over V equals PMM over RT, which is equal to our density. I doubt we'd have to do that. We could usually use PV equals nRT, solve for something we need, and then plug it in here to get that. Like they might have the molar mass, so you could solve for moles, use the molar mass to get mass, then plug it into density is mass over volume. Right? But this equation they don't give you, but they give you these other ones. Right? Dalton's law of partial pressures. That's the idea that the total pressure in a container is equal to all the pressures that those gases are exerting. Gases behave as if they're the only ones in the container. So we'll end up with PA plus PB plus PC, right, with whatever other gases are in there. So we can just add them together, we'll get our total pressure. Mole fraction is just like a percentage, we just don't multiply by 100. Right? So this would be part over the total. Right? Let's say our mole fraction is X of A is 0.25. And my total pressure is 2 atm. Well, that means that 25% of the pressure being exerted is the partial pressure of my A. So all I have to do, my PA is going to be my mole fraction of A times my total pressure. So in this case, 0.25 times 4, 0.25 times 2, ATM, what am I going to get? 0.5 ATM. Not bad. All right, so that's the idea of partial pressures and mole fraction. Kinetic molecular theory. First up, kinetic energy. All right, so kinetic energy equals 1/2 mv squared. That's given to us. We don't have to do calculations with it, but we'll have to do ideas with it. All right. So if we have two gases with the same kinetic energy, if they have the same average kinetic energy, what do they have else in common? They're at the same temperature. So kinetic energy is directly proportional to temperature. How is speed related then? Let's say we had the same gas at two different temperatures. If we have the same gas at two different temperatures, as temperature increases, the kinetic energy increases, right? What has to increase then for that gas as the temperature goes up? Is the mass going to change of something? What's going to change then? The velocity. The velocity is going to increase. So at higher temperatures, the particles move faster. That's our relation. What is the relationship between speed and mass if we have two different gases at the same temperature? Same temperature, same average kinetic energy. Which one is going to be moving faster? Which one is going to have a higher velocity? The one with the lower mass, right? So there's an inverse relationship there. Small particles moving faster, so they have the same kinetic energy. Big particles move slower, so they can have the same kinetic energy. Diffusion to fusion, what matters there? The size of the, let's go, for fusion, we got the pinhole leak, all right? And what's going to end up happening is the smaller gases, they're going to have an easier time getting through that hole. And what else about those smaller gases that we just covered? They're going to be moving faster. So they're going to diffuse and effuse faster than larger gases are. Ideal behavior. What does it mean to be ideal behavior? It just means that it behaves according to the ideal gas law. No, there are no ideal gases, but there's gases who behave ideally under certain conditions. When we say deviate from ideal behavior, that means I would plug in a bunch of values to PV equals nRT. I would get a measurement. The measurement of my calculation don't mesh. I'm starting to deviate away from what I should get. Why? What's happening? Ideal behavior is at high temperatures and low pressures. So at high temperatures, when those particles collide, they bounce off each other. They don't stick together. They don't have time because they have so much energy. They're just going to bounce off each other. Low pressures, that just means there's not a lot of gases in the system. The volume of the actual gas particles doesn't matter, is negligible compared to how much room they have. So where is it going to start to deviate? Low temperatures, those particles are going to start to stick together. If they're sticking together, they're not having those elastic collisions. There's going to be less collisions with the walls of the container. We're going to end up having a lower pressure than expected. Really high pressures, that means we're really dense gas. That means there's a lot of particles in there, right? We equated it to, you throw a few basketballs in the gym, that doesn't affect the free space of the gym. Those particles are negligible. But if I threw a few basketballs in the hood here, now that volume that's free to move around has changed because those basketballs are significant compared to the volume, that limited volume there, right? So